This is our May method seminar, so we're happy to have Jacob Konikoff today here with us, and he's going to be defending his final dissertation next week. And he's going to be sharing with us cross-sectional HIV incidence estimation approaches and challenges. And I'm looking forward to, this is a very relevant topic for us, so I'm looking forward to your talk. So.
Great. Well, and thank you very much for inviting me. I really appreciate it. And I guess some of the questions I want to highlight today are, why are we doing this? Why is estimating HIV incidence important? Why is it so challenging? It's actually been a subject of controversy for 20, 30 years now. And then some of the approaches that I've been working on and been working on with Dr. Brookmeyer, as we were just talking about, to sort of address those challenges. And just to fix notation, since there's a lot of different things people call incidence, in this talk I'm going to call incidence the expected number of new infections per year at a given moment in time among those who remain uninfected up to that point in time. So you can think of it as the rate at which new infections are arising from the susceptible or uninfected part of the population. There's at least a couple statisticians here. It's a hazard rate. It's an instantaneous failure rate, where failure is becoming infected with the virus. Some people call this the incidence rate, and they'll call something else the incidence. But we're going to use that definition for today. And why do we care? Well, I think there are two main reasons. One is tracking and surveillance of the epidemic, which has a lot to do with resource allocation. So if you know where the infections are occurring now, both you can try to stop them, you can try to curb the epidemic in those locations, and also you can plan for the future. So since HIV comes with this very long asymptomatic phase, the burden of the virus isn't going to be felt where the infections are happening now until much later. So something like HIV prevalence, which is the total number of infections in the population, sort of represents that burden, whereas HIV incidence is more the leading edge of the epidemic, what's happening right now, where those new infections are, and where the future disease will be. And the other main reason is prevention efforts or prevention trials to see if prevention efforts work. And if you're going to be running one of those trials, the first thing you're going to need to do is a sample size calculation. You're going to need to figure out how many people you want to include in one of your surveys. And that's going to depend on what the underlying incidence is. So you can imagine that if very few people are getting infected in your population, you're going to need extremely large samples in order to distinguish whether you've actually prevented infections or you just randomly got a bunch of people who were not infected. Whereas if, say, half the people in your population are being infected with the virus, if you're not seeing any infections, you're going to know pretty much right away, regardless of your sample size, that you're actually preventing those infections. So the underlying incidence will influence your sample sizes. It's also important for selecting where you'd want to conduct those prevention efforts, and also where you'd want to conduct a trial to see if those prevention efforts work. You want a high incidence location for the trial so you can limit the sample sizes, and you want to target populations that will most benefit from you conducting those trials. And then at the end of the day, when you evaluate those trials, you're going to want to see that you made a difference. You're going to want to show that you've reduced incidence, you've reduced the rate at which those new infections are occurring in the population. So three main approaches to measuring HIV incidence that are out there. One is longitudinal studies, which I tend to think of as sort of the most intuitive. You take a bunch of uninfected individuals, you follow them forward in time, see how many get infected, and that will tell you something about the rate at which new infections are occurring in the susceptible part of the population. Then there's changes in HIV prevalence, maybe a couple HIV prevalence surveys. Those are occurring all over the world right now, where you're having these large population-wide surveys. And say that in 2014, there were 1 million people in the US infected with HIV, and in 2015, there were 1.1 million. Well, then I know that at least 0.1 million new infections occurred in the US or entered the US population. And then there's cross-sectional studies, which is what the main focus of today's talk is going to be. But before I get to that, I want to sort of point out why people don't use the first two, or why people even think about these cross-sectional studies. So the longitudinal studies have three main complaints that have been sort of brought against them. One is selection bias. HIV predominantly affects more marginalized and stigmatized groups in the population. So when you're trying to get people to sign up for these studies, or trying to bring them in for longitudinal follow-up, for all these repeat visits, it's unclear that you're going to be able to get individuals who are in some way, people take issue with the word representative, but in some way representative of the population that you're interested in. even if you get those people into your studies, who's to say that you're going to be able to actually follow them over time, that you're going to get them back into your studies? You're going to have issues with loss to follow-up. You might have certain biases there. Let's say those people who are engaging in more risky behavior are A, more susceptible towards infection, but B, also more likely to drop out of the study. Then you're not going to be able to properly estimate incidence. And the third one I find really interesting, which is that in some of these studies, a component is counseling. You bring people in, you bring them in for these follow-up visits, and you try to encourage them to wear condoms, to engage in safer behavior. That's great for the people in the study. It's terrible for the study itself. If you actually reduce the number of infections in your study pool, you're changing the quantity you're trying to estimate. It's no longer representative of the population, and you're not going to be able to estimate incidence. For changes in HIV prevalence, if I told you there were 1 million people in the US last year who were infected with HIV and 1 million people this year, you wouldn't tell me that no one was infected between those 2 years, even though those numbers are the same, because who's in the pool is changing, right? There's immigration and emigration. People are coming in, people are leaving, and another reason why people are leaving is they're dying, and people are dying at quite a different rate. You know, the relative survival rate, I should say, between those who are infected with HIV versus the rest of the population can be quite different, and also changes over time as we, include, we get more people on treatment, we have better healthcare systems that are more equipped to deal with it, and it turns out that that relative survival rate, even if you estimate it just slightly off, it will completely blow up these estimates of incidence, and you won't be able to tell what the true underlying incidence is unless you get a very, very accurate estimate on this relative survival rate. So you've sort of created a problem that's even more difficult than estimating incidence to try to estimate incidence. I think some people use these prevalence surveys in larger models that try to combine all the different methods, but right now the work I've done and I've seen other people do sort of say don't use them on their own, it's not worth it. Which brings us to the cross-sectional approach, which is what I've spent most of the past 5 years working on. And I'm going to start by just presenting it the way that my advisor, Dr. Brookmeyer, originally introduced it. And the idea was you're going to avoid this longitudinal follow-up by going into the population at a single moment in time and taking a very large random sample of individuals from the population. Then you're going to use biomarkers, markers in people's blood, in order to learn something about the recent infections. And the way you're going to do that is first you're going to look to see who's infected with the virus. You're going to look for a segment of the virus called P24. And those people who have P24, we know they're infected. They're shown in red, or sort of a red and a maroon, I guess. And those who do not have that P24 are uninfected. So that uninfected are going to tell us something about the size of the susceptible part of the population at that moment in time. That's half our equation, right? We're looking at the rate at which new infections are occurring in the susceptible part of the population. The other half of our equation is new infections. So how are we going to learn about new infections? Well, immediately following infection, when you can actually detect that P24 antigen in the body, individuals will not yet have an antibody response. They will still be gearing up their immune system. They'll still be starting to fight the virus. They'll have yet to seroconvert. And we can look for those people who have the P24 antigen, but no detectable antibody response, who are still antibody negative. And we'll know that those people were infected in the recent past. We'll group them into what I'll call an early disease stage. That stage is not about how long they've been infected. It's not these people have been infected less than 3 weeks. It's that they have the virus in their body, but they have not yet seroconverted. They are antibody negative on a standard antibody assay. So we know they tell us something about recent infection. They may not be all the recent infections of the population, but they're associated with recent infections.
So what's the average time frame between infection and seroconversion?
It's about 22.5 days, and I'll get to that shortly. But there is quite a long tail even in this.
And is this like the D2 and ELISA stuff that they came out? Is that the same concept?
It's related. So that's sort of, there's been several iterations of this. I like to start here, which is the first iteration, because I think it's the most intuitive, because those people really are recently infected, right? Those people really were infected within the past month. It's kind of obvious why they tell you something about recent infections. As we'll get to shortly, these detuned ELISAs, the BED assay that's very popular, there are people, for those who we mark as recent, who have actually been infected for 2 years, 3 years, 4 years, and it sort of becomes less intuitive. So I'll start here, and I guess when we get there, we can talk a little bit more about that. Sure. Another question? No? So then how are we going to actually estimate incidence? Because we don't have necessarily the number of people who are infected in 3 weeks or something like that. Instead, we have these number of cases in the early disease stage, X. We have these number of uninfected samples, N sub U. And then if we know one more very important parameter, how long people are spending, that's the question you asked. Here it's 22.5 days was the estimate in the original paper. We can use this very famous relationship from epidemiology that in a steady state, prevalence is equal to total incidence times mean duration. So if you look at that and you just move that N sub U, let me actually try to use this. Let's see, if we move those two over, am I going to have to erase that for the next slide? Yeah, not worth it. Oh, I don't even know what that's about. Touch the screen. Oh, I see. OK, well, I will not use the screen in the future. But you can move over the N sub U and the mu, and that will give you an estimator, a rule for calculating incidence, which is we'll find the number of people in that early disease stage, we'll divide by the size of the susceptible part of the population, and then we'll divide further by mu. So sort of as an example to see what mu is doing here, let's say we find 1,000 uninfected people in the population in our sample. That tells us something about the size of the susceptible part of the population at that moment in time. We found 50 people in the early disease stage. That tells us something about those recent infections. And let me, for this example, just to make it easy math, people spend half a year in the early disease stage. So then you'd say, OK, we have about 50 divided by 1,000 infections per half a year. Mu is giving you that sense of time. If you divide by the 1/2, this 1/2 is playing the role of the mu there. Then you'd say, oh, I have 100 divided by 1,000 infections per year, which is our unit here, right? The expected number of new infections per year in among those people who remain uninfected up to that point in time. So that's sort of a simple example of why that estimator sort of intuitively works. There's actually a fair number of complicated things going on behind the scenes and a bunch of assumptions, which we'll sort of break down once we get to the detuned ELISA and that type of assay. So something I wanted to point out before I continue is that in this estimator, in this rule for calculating incidence, if we look at the cross-sectional study, if I look for X, I see, OK, I have these 2 people there. Those are the people in the early disease stage. I look at NU. That's this blue. It's the size of the susceptible part of the population. But nowhere in that picture is there anything about mu. There's nothing about how long people are spending in that early disease stage. There's no dimensionality of time because the cross-sectional survey happens at just one moment in time. So I don't know what it means for those recent infections to be recent unless I go ahead and estimate mu, which is exactly what your question was. So how do you do that? You go and you find stored blood samples of people in the population who have been collected for other reasons. You find people who were uninfected, became infected, and you see how long did it take them to develop that to seroconvert, to move from infection to the point where you can detect that antibody response. So researchers did it. 22.5 days is the actual amount. 1 month is an approximate there. It's an estimate anyway. And that was really good, because it meant that this was associated with recent infection. We were really learning something about recent infections. The problem was that when you conduct a cross-sectional survey, which is represented here by this dotted line, it's very easy to miss these people, right? They're only in that stage for a short amount of time. The sample sizes you need to implement this methodology as it was originally proposed were huge. Also, the P24 antigen, was very expensive to detect. So this wasn't a practical approach, but researchers weren't yet ready to throw it out. The thought was maybe we can just redefine what we mean by early or this early disease stage in order to lengthen how long people are spending in that stage, and that will allow us to still use this method. And that's where the detuned assay came in, or what became very popular was this BED IgG capture enzyme immunoassay. And what they did is it's the same general idea. We're going to, instead of measuring from infection, we're going to measure from seroconversion, which is only a couple weeks after. and we're going to say that people who have not yet seroconverted are all at risk for seroconverting, even if you are infected. So we're changing the at-risk group a little bit, but then we're going to say how long does it take people from seroconversion until you pass a certain cutoff on this assay that's measuring recency. So this BED assay is measuring the strength of the immune response. It grows over the course of infection. If you're below a certain cutoff, we're going to associate you with recent infection because your immune system hasn't geared up past that point. If you're above that cutoff, your immune system's geared up past that point, and we're going to associate you with long-term infection. So if we do this, people spend a lot longer in the early disease stage. It's no longer telling us something about this instantaneous hazard rate, this instantaneous rate at which new infections are arising from the susceptible part of the population. Instead, our estimator is actually measuring incidence in the past. And the point in the past, I'm going to denote psi, or we're going to call it the shadow, where this shadow is a weighted average of the amount of time prevalent early disease stage cases have spent in that early disease stage before the survey. So if you look here, we have these 4 people. 3 of them are in the early disease stage at the time of the survey. So how long they've spent in that early disease stage before the survey will determine when we're approximating incidence, which is to say that since these people were infected at some point in the past, they don't tell us information about what the current incidence is. They don't tell us information about that instantaneous hazard. Rather, they tell us something about what the incidence was when they were infected. They give us information about infections at the point of time when they were infected. The exact formula for what that is a weighted average, which you don't have to memorize. There's no quiz at the end, but it's based on this phi of t curve, which is a probability that persons will be in the early disease stage t years after seroconversion. It's sort of a survival curve, how long you remain in the early disease stage following infection. So you could think that most people, let's say, spend 3 months, 4 months, but some people may spend a very long time in that early disease stage just because people gear up and fight the virus differently, right? Some people are elite controllers. Some people will not mount an immune response that will allow them to cross that threshold for a long time. So the weights, how long or how much emphasis, I guess, we put on that individual's infection who's in that early disease stage, if we go back to this thing, is based on the probability we'd find someone who was infected that far in the past. Yeah?
Maybe I should let you finish the sentence, but because the psi doesn't have an index, I was thinking if you're talking as if it could be different for different people.
Psi is the weighted average for the population. It's a population level parameter. But the phi of t is also a population parameter, but that's going to be made up of each individual person will spend a different amount of time in the early disease stage. So you weren't here at the time, but the early disease stage is defined by the biomarkers. So you're in the early disease stage if your biomarker response, in this example, your BED, is less than 0.8. It has nothing to do with the fact that you were infected, let's say, less than 3 weeks or 6 months or whatever you might traditionally call a recent infection. Rather, it's completely defined by the biomarkers. And then what we're doing here is trying to associate being in that early disease stage with what it means to be recently infected. So there's sort of an association between being in that stage and being recently infected, and we're trying to quantify that association. And this curve here, this probability of remaining in the early disease stage, is sort of how we're going to do that. Does that help at all?
Yeah, so phi of t is a distribution.
It's sort of a survival curve. So it's how long on average the population, but you could think of each individual survives for blank amount of time in the early disease stage, where surviving is remaining early and not moving into the long-term group.
I guess another variation on the question would be you think of phi of t as a mixture of
Sure.
something. So there's a mix in.
Yeah, so if you have different populations, that's exactly how you could maybe handle it, where you could break up the variability you see in how long people spend in the early disease stage based on certain characteristics, certain covariates. You could.
Or there could be 2 or 3 or 4 types of people.
Sure. Those are all possibilities. We're going to stick to a simpler, more general, where this is just representative of the population right now, but that's definitely something people look at. So this phi of t curve, which is the survival curve, actually is also how we determine mu, how we determine how long on average people spend in the early disease stage. It should make some amount of sense that how long people spend over time is related to the average amount of time. If you know any survival analysis, the area under the survival curve is always the mean survival time, which is how we get that relationship. So remember, mu is going to be the average of these 4 different things, whereas psi has to do with how long in the past people were infected, and that's going to be when we're estimating incidence. So in order to recap the introduction here, here's our cross-sectional incidence estimator. It is telling us something about the rate at which new infections are occurring in the susceptible part of the population. Therefore, it's a function of x, the number of people we find in that early disease stage, and sub u, the size of the susceptible part of the population in that moment in time. And then these 2 key parameters, mu, the average amount of time people are spending in the early disease stage, and psi, the time in the past when we're estimating incidence. And those are both determined by phi of t, which is the probability that persons will be in the early disease stage t years after seroconversion. So I wanted to now look at some of the biomarkers that have been used. I'm not actually going to look at the detuned assays, because those are sort of similar to the BED. Yeah?
I was just curious, what's the average time to seroconversion versus the average time spent in the weak antibody response?
So in this definition, also here, just give me one more slide. It's about 200 days with the BED. That's what people tend to estimate, at least, and I'm going to talk about that shortly. But it's quite different. So it's almost 10, let's say 10 times as long, which drastically, I'm going to hopefully at the end have a little time to look at sample size calculations, and you'll see that you can drastically reduce the sample sizes you need, even by doubling the amount of time. Just think, an easy way to think about it is that, you know, if people are spending an entire year in the early disease stage, it's much easier to find them than, let's say, 1 day, right? Or even 1 minute. If people are just spending 1 minute, it's going to be very hard to pick up those people, right? That would tell you more about recent infections. It would need less statistical modeling, but it would just be, it wouldn't be practical. Whereas ideally, you'd want something like this. So the BED, in fact, the reason I'm going to focus on that instead of the detuned is because it became extremely popular. It was used, for example, in the United States, Bangkok, China, Cambodia, Sub-Saharan Africa. It was used all over the world. People were really interested in using this BED assay with this mean window period that various people estimated, all somewhere around 200 days. However, in sort of the height of its use, UNAIDS came out with a statement that said they don't recommend using it. And the issue was that there is evidence that the BED capture immunoassay not only gets these recent infections, but also extremely late stage infections. So at the end of infection, when people are dying, their immune systems are collapsing, right? Like that's why we see these CD4 cell counts drop below 200, which is clinical AIDS. And when your immune system collapses, if you're trying to measure recent infections based on the immune system, they'll look like they're not infected again. They'll look like they're recently infected at the end. So it was, the BED assay was as much telling people about recent infections as it was long-term infections. And this, I think, also mentions antiretroviral therapy. I'll also get into that. That can also really change the natural course of the immune system, which makes using this assay sort of a little dicey. So we went about evaluating this on our own because we were curious, because people were getting this estimate of 200 days. But if people were really, you know, at 8 years being included in this early disease stage, you'd think that it'd be much longer. You'd think that there'd be some average of the amount of time people are spending in the early, who are truly recently, and some average of these people who are way out in infection, who are actually on the verge of dying. So we got a repository of samples with known seroconversion dates, and we were able to assay all those samples with various biomarkers. And that work was done at Johns Hopkins by Dr. Susan Eshelman and Dr. Oliver Leyendecker. The samples we have came from 3 different trials in the United States: the HIV Network for Prevention trials, HivNet 001, which was a vaccine preparedness cohort study. So they were looking to see, could we conduct a vaccine trial here? We want to know what the underlying incidence is. The AIDS-linked to intravenous experience, a live cohort study, which was a study of injection drug users, and the multi-center AIDS cohort study, the MAX, which a lot of people at UCLA are involved in. It's at 5 different centers around the United States. It's predominantly men who have sex with men. We had 1,782 samples from 709 individuals, all with these known seroconversion windows. So we don't know exactly when they seroconverted, but we have it usually within 6 months. And the samples were taken anywhere between 14 days and 8.6 years after seroconversion, which is going to basically allow us to measure this phi of t curve that we care about, how long people spend in that early disease stage, out to 8.6 years. So just to show you some data, these are just the actual raw proportion of people we're finding in the early disease stage at the various point in time. So you can see that this is not even that high early on. It's somewhere around 60%. And then it sort of drops off and then kind of spikes up at the end, which is when these people are re-entering it because their immune systems are collapsing. So we modeled this. I'm not going to actually get into how we modeled it. That you can look forward to for my actual dissertation talk. But what we found was that its mu is actually around 1.5 years. It's not close to this 200 days that we were seeing in the literature everywhere. And the reason why there was such a discrepancy is that people were not taking the integral of this curve. Instead, they were finding individuals in the population and seeing how long that individual took to exit. So they weren't at all picking up the possibility that that person might re-enter the early disease stage. Right? If you just follow an individual forward, you see, oh, it took him 3 months before he left the early disease stage, or it took her 6 months. You're not going to see if 8 years later they're back in the early disease stage. You're going to miss that whole component. In fact, people who had low CD4 cell counts or were on antiretrovirals were excluded from a lot of these studies that estimated what the average monotype people are spending in the early disease stage is, which meant that these estimates weren't actually reflective of the population. Now this sort of gets into what you're talking about. You might have 2 or 3 kinds of people and you could weight it. You could say, oh, it's 200 days for people who are not experiencing immune collapse or not on antiretroviral treatment, and then you could estimate it differently for those who are, and you could weight. But for now, let's just focus on the fact that this doesn't look very good. In fact, so this is based on the integral. I just took it out to 8 years, so this might be even longer, but it's certainly much longer. More importantly, when are we estimating incidence? More than 3 years in the past, if at all. This is actually an approximation. It's not exactly the incidence 3 years ago, and the larger this number is, especially when this tail is high, the worse of an approximation it does. So really, I don't think you can use the BED assay to measure incidence at all. I agree with you in AIDS. So people said, well, can we make this work? Currently, the CDC is pouring a lot of money into this. Bill and Melinda Gates Foundation is pouring a lot of money into it. 2 recent assays that have come out are the LAG Avidity assay, these are both also measures of the immune response. This is measuring the avidity or strength of bonding to certain peptides in the immune system. And this is a comparison between antigen binding between a treated substance and a not treated substance. So you're trying to normalize things. But kind of what's important there is these are both measures of the strength of the immune response. So it's still the same general idea. They're just trying to find maybe a part of that immune system that will be less susceptible to immune collapse at the end of the disease or less susceptible to antiretroviral treatment. So how do these brand new assays do? Here's the LAG avidity with the proposed cutoff. It actually seems to be lower later on, but also lower earlier on. So what we sort of ideally would want would be like 100% in year 1 and then nothing after, right? So like a perfect association with recent and then nothing after. You're never going to have that. You're never going to tease out the entire tail, but you're going to try to keep it as low as possible. And you certainly want this higher up if possible. So there was our fit. We got 0.6 years. So that's a reasonable mu. That's something that we could work with, like the 200 days. But again, the shadow is too high. It's 2 years. We want to learn something about recent infections. We don't want to learn what incidence was approximately 2 years ago. We want to learn what incidence was approximately a few months ago. The biorad avidity assay is a lot better. It's much higher earlier. These are plotted, by the way, at the midpoint. So it's halfway between there and there of the data in that window. So it's a lot higher earlier on. It also kind of goes down 0.8 years, but still the shadow's kind of unacceptable. Sort of the goal of NIH when it funds these studies is within 1 year. Within 1 year. I don't know why 1 year was decided as recent, but that's what people deem acceptable. This is sort of unacceptable. So here's a comparison. You can see how much worse the bed, which was used really all over the world, does than these new assays. But these assays still are not quite performing as well as we would have hoped they would have. So if you look, here are profile plots of the two better assays. Let's call them that. There are about 10 different ones out there nowadays. This is the log of the lag avidity response. So it kind of has this pattern here, but there's a lot of noise, right? So ideally, I'm going to use this again and regret it, but ideally, we'd see something like this, and then we'd be able to say, OK, here's recent infections, and then that would group these people away from those people, right? You almost have that here, right? Oh, I did black. That was a mistake. Yeah, I can't hit. What?
Do it one at a time, so put one down.
Put one down?
Oh, the ink's gonna dry.
How come that's still black and not red?
Put it on the black.
You want to put it on the black?
It's sensing
Yes.
the fake marker.
It should be red now.
Nope. OK.
Put the eraser down too.
Put the cap on.
The cap on. There's no cap.
Here. Jacob, the eraser. Put it there.
All right.
Should be red.
Totally worth it. All right. So we see this. We almost, here we see like a much more distinct pattern, right? And we could let's put that down. We could do a much better job separating recent from not recent with this sort of cut, right? Because there's less noise here. However, there still is a fair amount of noise there. I'm going to have to erase this before I move on. So the question is, though, what if we didn't limit ourselves to these serologic assays, which are based completely on, this antibody response or the strength of binding of the antibodies? What if we instead included things like CD4 cell count, right? So if you want to exclude people who are at the end of infection, let's remove those people who have CD4 cell counts below 200. Let's remove those people who are on antiretrovirals, who have viral loads below 400 copies per microliter of blood, right? That shows that they're virally suppressed. So if we remove those people, here's what we get. Much cleaner patterns, much easier to model, much easier to separate the recent infections from the long-term infections. And that led us to sort of look at what we call multi-assay algorithms, which are sequential algorithms that use 4 different assays. You could potentially use more. Here's what we sort of looked at. We're going to include CD4 cell count. It's going to have some cutoff. If you're below that cutoff, let's say 200, that's clinical AIDS. Your MA negative, which we're going to say that's what's associated with long-term infection. MA positive is going to be associated with recent. If those people are not long-term infections, then we're going to move down to this, and we're going to run the biomarker-based assay on them. Now, if they're above the cutoff here, because this is the antibody response. If you're too high, you've had longer to progress. We're going to remove you. If you're below, keep going. We're going to give the lag viral load. Okay? The advantage of this type of algorithm is it saves a lot of money, right? Because you test all your samples here, but only a subset here, and then only a subset, only a subset. This is about $50 per assay run. These are about 20. This is 100. The reason why this is first and not here is CD4 has to be run on live blood. The other is you can store the samples and run it later. So this has to come first. You want to basically put your most expensive assays last so they're not run on samples. That make sense? The question now is, how do we choose the cutoffs? How do we decide what's recent, what's not recent, or what's this early disease stage? How are we going to define it? So we basically did a brute force approach where we looked over all possible. This is definitely the most dense slide I have. We looked over all possible cutoffs in sort of a reasonable range, and we had 4 different criteria we wanted it to meet, and among those we want the one with the largest mu. So the one that has the largest mu will more or less have the least amount of variability in the estimator, because we're going to get people in our samples easier. It's going to be easier to find them. It's going to reduce our sample size. So we want the one with the largest mu, but we want to make sure that we're going to be able to estimate it. So we're going to require that that phi of t curve is at 0, less than 0.001 by 8 years, because that's where our data ends. We don't want, I'll skip that one for now. We don't want the upper 95% bound of the confidence interval for the shadow or psi to be more than 1 year, because we want to be certain that we're estimating in the past year. And then sort of as a trick to making this easier computationally, we're just going to require that the point estimate is less than 250 days. We found that basically once they got up near 250 days, they always went over, and it was very computationally intensive to calculate this, pretty easy to calculate that. So basically we're trying to find an algorithm that has an acceptable shadow, which we're defining more or less to be a confidence interval whose upper bound is less than 1 year. And among those who are acceptable, we want the one that has the largest mu, because that's going to control the variability.
So going back to the
Sure.
algorithm flowchart, is there any, where's the antiretroviral therapy?
So it's coming in the viral load. We're going to use low cutoffs that would mean viral suppression. So there are some people in the population who are naturally going to have less than 400 copies per microliter of blood, but most people in the population, if they have that, will be on antiretroviral therapy.
But conceivably, people could still be on antiretroviral therapy, but still not achieve viral load suppression.
That's true. So then the question is, how much is that affecting the progress of these biomarkers if they're not actually suppressing? So it sort of seems like the danger that where these fail is when they are suppressing. So that seems to be the role that's played there. I just spoke with our colleagues at Johns Hopkins, and they have all kinds of new ideas to maybe tackle that in a different light. But this is one approach, I'd say. But that's a good point. So here's, among those people who had the acceptable shadow, here's sort of what we get over this dense grid. And that's our winner. This is the one that has the largest estimated mu among those with acceptable shadows. The largest amount of time people are spending in the early disease stage among those MAAs, among those algorithms that are likely estimating incidence within the past year. So what does it look like? It's here in MA1. It had an even lower cutoff for CD4 cell count, 50. So those are people who are really far along, right? They really have lost their immune system. The bio-rad avidity is at 85%, lag is at 2.9. Those cutoffs are not so naturally interpretable. This viral load of 400, people use that all the time to mean viral suppression, right? So that's who we're excluding. The mu here was estimated to be 0.4 years. So I don't know, 160 days, a little less than 200, but certainly much better than that 22 days we were originally working with. We also looked, MAA2 here is an MAA that doesn't use CD4. We allowed for it to include viral load. It didn't need viral load. So there is some thought, having talked to some clinical people, that very low bio-rad avidities are not sensitive to that viral load issue. So if you're going to have a low enough cutoff here, you no longer need viral load. The advantage here is cost. It's, these are $20 a pop. This is 50, this is 100. These are much more expensive. We've done some work, and it looks like this would be about 3 times as expensive to use in the field as something like this. And then the third MAA, I've included the way we searched for that was the same criteria, but we allowed it to include at most 1 of every 1,000 people infected more than 1 year in the early disease stage. So it could only misclassify, if you will, 1 in 1,000 people after 1 year. So that should have the lowest amount of bias. You're giving up a little bit in mu. It's a slightly shorter mu than this sort of optimal in a general sense, but you can also see that the shadow is much shorter. And when I talk about bias in the estimator shortly, you'll see that it performs quite well. So just to sort of visualize what these different algorithms are doing, this is among people who are not virally suppressed. I've plotted all the different data points we have, and the early disease stage is this pink box. It's kind of hard to see those who are in front. So you can see here that it's basically all white or lighter gray, so it's including, this is MA1. So it's including mostly individuals who are recently infected. You are missing some of them up there, but very few people have been infected longer, and no people infected after 5 years are getting caught in that early disease stage. For the second one, it's a little easier to visualize because we only have 2 algorithms. You can also see sort of the same story. A lot of white, a little lighter gray, none of these like black type dots, which are the people really far, which really end up biasing these estimates a lot. And then for this low bias, the third one, it's all white because that's how we designed it. It's all white. So comparing the phi curves for these, you can see that the one that just uses the 2 assays, MAA2, has sort of the longest time to get down to really start excluding all noticeable people because you're not using all 4 assays. The low bias one is this orangish one. That's the one that we're excluding people really early on. You can see it gets down to 0 very quickly, which is sort of the behavior we want. But pretty much the tails are pretty low in general with these. And I should have put the bet also, but if you remember, the BED was out at like 20%. I have no idea where I am. OK, BED, I don't want to write on that. It's going to be too much of a hassle. The BED was at 20% out at 8 years. These we're talking fractions of a percent. So there's a big improvement by including these additional assays. And as sort of a further check, we got another data set, which is from the Johns Hopkins HIV Clinical Practice Cohort. It was 500 samples from individuals infected more than 8 years. We don't know exactly how long they were infected. We don't have any idea about their seroconversion time. We just know that they had a positive test more than 8 years ago. And we checked and made sure that for these 3 MAAs, that all of them were excluded. We're not including any of those people. And they checked out, which was good news. So I showed you 3 different possible MAAs. I explained that you might choose the middle one mostly for cost. But briefly, I think I have like 15 minutes here. I want to talk about 2 other considerations because there are a lot of viable MAAs, and it's sort of hard to say, oh, this one has 0.4 for mu, how long people, and this one has 0.39. How do I decide what I want to use in what place? So one thing to look at is the bias. So this is our estimator, and if you subtract off what the true value is and divide by the true value of the incidence psi years ago, you'd want to know how close am I getting. So I call this the relative bias. So we simulated epidemics. The methodology, there's 0 bias if the epidemic looks like this, if it's linear. In all the other cases, there will be bias in the estimator. So here's the bias. I should have labeled these. This is the low bias one, not surprisingly, all the way down. This is the optimal one, and this is the 2 assays. So you can see that when you use the fewer assays, you get the most bias. And this is Epidemic A, which is this decreasing epidemic. It turns out that which direction the relative bias goes, you can determine by the concavity of those slopes. So as you'd expect, I'm all negative when I switch to this concave up. This is Epidemic D. I think I mislabeled that. Yeah, I apologize. Here, this is constant because it's exponential growth. And it turns out because the exponential has that nifty property that its derivative is just a constant times itself, that it won't matter where you are in the epidemic. But again, what you see is almost no bias for the low bias, that we just trimmed that tail right away on that T curve. This is that optimal one, and this is the 2 assays. So we are losing something in the total bias, but these are not so, so this would say, for example, that if the difference between my actual assay divided by the underlying epidemic divided by the underlying incidence is only 0.05. It's not so bad. And I'm going to have a simulation at the end where you actually see some of these differences. And then in that sort of curvy epidemic, you'll get that it switches directions based on the concavity. So I guess the point I want to make up, the main point of these slides, besides the fact that they're colorful, is that you do lose something by using those 2 assays. You save on costs, but you by far have the most bias. And here you give up something in mu, how long people are spending in that early disease stage, but you get no bias. So one of the messages, I think, is that you might want to select which MAA you'd use based on what you'd expect to sort of see. If it's a very rapidly changing epidemic, you might want to give up something and need, require larger sample sizes, but have no bias in your estimator. If you're approximately linear, then go ahead, use the cheap one. So then the last thing I wanted to cover was a little bit about sample sizes. I'm not going to actually derive the formulas for you, but I'm going to try to give you sort of a general idea. So one goal you might have is you're conducting one of these trials to estimate incidence, and you want to have a certain level of precision, where I'm going to define precision to be the width of the confidence interval I'm going to get around the underlying incidence divided by the underlying incidence, right? So that gives me a sense of how precisely I'm estimating incidence, okay? So I want to control that, I want to set that, and then I want to know how many samples I need. the way we're going to do that is we're going to assume that the people we find in that early disease stage follows a Poisson distribution. I'm not going to get into this too heavily, but Poisson is used when you're measuring rare events. You can think that finding someone in that early disease stage is a rare event because most people are not infected. And of those people who are infected, only a small proportion are recently infected, right? So this is just a counting random variable of rare events. Its mean just comes right out of this prevalence equals incidence times duration relationship. That's all you have to know there. What's important, though, is that x follows this Poisson distribution conditional on knowing mu, which is in its mean, but we don't know mu. We have to estimate mu, right? We don't know how long on average people spend in the early disease stage for the whole population. We don't know that exactly. We estimate it, and when we estimate it, we actually get sort of a distribution. So I wanted to directly incorporate that in to our calculations, so I put a gamma distribution, which sort of changes things. And that will depend on which MAA I use, will depend on what this distribution is, right? Because each MAA has its own mu. So here's the formula. You don't have to know anything about it. The only thing I want to point out here is that everywhere in this formula where there's a sample size, it's being multiplied by the underlying incidence, which means that the sample size is inversely proportional to the underlying incidence, which sort of quantifies directly that concept that I said at the very beginning, which is if there are smaller sample sizes, you need more people. If there are larger, if the incidence is smaller, you need more people. If the incidence is higher, you need fewer people. And it turns out that that relationship is exactly inversely proportional. So here are 4 different possible distributions for that mu, for that unknown how long people are spending in that early disease stage. This red curve is the mu associated with that optimal MAA, MAA1, that had a mean of 40. So here's its mean of 40. The variance was 0.001. This black curve would be a case where I did these sample size calculations, but I assumed I knew how long on average people were spending instead of quantifying the fact that I'm actually uncertain. Right? So I'm just putting a point mass there. I'm assuming I know exactly how long people are spending. This green curve is a case where there's a lot more variability. That would represent a case where I didn't do as good of a job estimating mu from the target population before conducting these studies. This blue curve sort of answers that question of why does it matter if we have a 200-day mu or a 22-day mu. I've just shifted the red curve over. And if you look at the sample size calculations, I'm going to first focus on these 3 curves that have the same mean. You can see that if we have more variability, I need much more larger sample sizes for any desired level of precision. So this is more and more precise moving down the y-axis. So these are higher and higher sample sizes. I undersample if I ignore the fact that I don't actually know mu, right? So the black curve is pretending like I don't know it. The red curve or the green curve are situations where I'm quantifying my uncertainty. And also, you can see these actually asymptote, which is to say that in this cross-sectional estimator, there's 2 sources of information, right? There's the information you're getting that you're bringing in beforehand about estimating mu, about estimating psi, and there's also the information in the survey itself. And if you don't do a good enough job in one location, you can't make up for it in the other. That's what these asymptotes mean, right? If I have too much variability in my estimate of mu, I'm never going to get certain levels of precision. If you put in this blue curve, you can see that you have lower sample sizes across the board. And that was just doubling mu. And some of these, it's kind of hard to see because these asymptote, but these make very big differences. So just having a longer mu really, really goes a long way. Here's some actual calculations for the MAA1. You can see that if the incidence is low, these are absurdly high sample sizes you need. It's very unpractical. If the incidence is high, you can get any kind of level of precision, meaning that it's just harder to measure smaller quantities. If you want to try to find a very low incidence with a lot of precision, you're going to need a lot of people. So sort of certain parts of this table, I'd say, are inaccessible. The other situation you might be in is if you're doing a prevention trial where you have 2 measures of incidence, right, at times T1 and T2. And you're trying to estimate incidences I1 and I2. And you want to know, are they equal? That's our null hypothesis here. Or is one bigger than the other? So that I'm going to let be R. And I'm going to define these in terms of a design parameter, which is the ratio of the 2 sample sizes. Okay? And I'm just going to show you the results here. I'm not going to show you the formula because it's complicated again. It's the same incidence is inversely proportional. We get the same result. If you focus here, the these are the 4 curves. So if you look, this is the curve where I just shifted the mu. I doubled it. I made it so people spend twice as long. And you can see that these numbers are much, much lower than the other numbers. So doubling the mean really reduces how long or how many samples you need. This is, you need to multiply these numbers by the underlying incidence to get the actual sample size. So if the incidence was 1% here and you wanted to detect has incidence doubled, you'd need, lost my place, you'd need 6,810 people, okay? So I don't want to get into this too much, but it's sort of the same general idea that if you can double mu, you can really reduce the sample sizes, that if you don't quantify the uncertainty properly, then you're going to wind up undersampling. All the things that happened in the one sample case happen here again. It's definitely should have cut down this table. I apologize for that. We ran these fake epidemics that we use for the bias. We also ran them for these sample size calculations. And in this column, I have what the actual incidences were that we were comparing for these power computations, right? So I'm comparing 80% to 30%. I'm trying to see if I actually see that difference. So this was what the true incidence was. In this column, I have what the actual incidence is being simulated because there's bias, right? So here, the actual incidence is 30%, but on average, I'm guessing that it's 29% because my method's biased. If you look in C somewhere, oh, right, sorry. Ignore that. What you'll see, though, is that the power is supposed to be 90%, and it's pretty much everywhere except, again, in that epidemic that looks, I'm just going to leave this up here, but that looked like this. Then you start to really struggle a little more. That's these two. You start to lose out on the power because it's harder when something changes. Really what happens here is that this number is larger than this number. And this number, so these two numbers are closer together than those two numbers, right? So the bias is going in both directions because of this curve. Whereas in the other cases, the bias all shifts one way, so you don't lose out in sample sizes. But when you actually are trying to, you're guessing that my alternative hypothesis is further apart than it truly is because of the bias, then you start to lose out on these power computations. There's also these CI coverages, that's sort of evaluating the one sample case. Those should all be 95%. You can see that you do the worst when the underlying incidence is really low, because it's just really hard when the incidence is low to learn things. So one way to do this is instead of taking a large sample from the population, when these large cross-sectional, is to actually target specific areas and then weight them, which is something that people have been tossing around for a while. So I kind of want to erase those, but also don't want to. So here are some conclusions. The cross-sectional studies are measuring incidence in the past. They don't actually measure the current instantaneous hazard rate. You need to properly estimate these things. So that was this whole problem with the BED, why it wasn't actually working. It overestimated incidence all over the world. Multiple biomarkers can really help. They can sort of take away a lot of that noise. You need to account for the uncertainty in mu. That was the less than stellar job I just did on those past few slides. And that some of those sample sizes can be prohibitively large. They can be quite large, especially when that incidence is low. When you're trying to detect a really small, those are in the wrong place, probably freak out. When you're trying to take a very small change in incidences, or you want a lot of precision. And then I just wanted to thank the people who provided the data, the ALIVE study, HivNet 001, Max, and Johns Hopkins HIV Practice Clinical Cohort, and my colleagues and co-authors, I should say, Dr. Oliver Landecker, Dr. Susan Eshelman, and Dr. Ron Brookler. So thanks. Any questions?
That was very good. I really enjoyed your talk. So I wanted to kind of ask you a question about different types of algorithms that you use, and the ones that are not as certain, the one that has the most amount of bias.
Sure.
I'm thinking about these programs that we're doing in like low and middle income countries. So they have existing surveillance that they do, and they're doing it like every 2 years or so.
Okay.
And what they find is they're concentrating on these emerging epidemics. So for example, in Vietnam, they're looking at these, serial behavioral surveillance, and they're looking at prevalence every 2 years, and it's looking like the prevalence is increasing.
Okay.
And the prevalence is pretty high. It's like, some pockets are over 20%, for example.
Okay.
And then, example, in Thailand, they've seen it consistently increasing every 2 years. So it went from 17 to 25 to 29%.
So you have a bunch of these serial prevalence surveys.
So and then when you talk about the shadow, and even the worst one, you're estimating incidence from 2 years ago. So kind of looking at like these behavioral surveillance that they're doing anyway, in terms of incorporating this type of algorithm to estimate incidence, although it's like, not what's happening right now. I feel like there's some utility to that.
Right. So I think also if you're doing maybe like a prevention trial, if you have the same, as long as your bias goes the same way, you'd still see a difference, right? The problem is, or one potential problem is, you can see how this bias grows a lot over here, and that's just with this tiny little difference in the tail, right? The more and more tail, the more and more bias you get. So I would definitely be nervous about using something like BED that's been shown to misrepresent over and over again. Something like the LAg Avidity, Bio Avidity, yeah, definitely I think that would be acceptable in that type of situation. And you're not going to cost yourself too much more by using that.
The burden of HIV, it's like the majority falls outside of the U.S. and the cost is an important factor. So
yeah, definitely.
If that's like the cheapest way to estimate incidence.
Right. It's definitely, so sort of what we need is some universal theory that, like a utility function that says, how much do I care about cost, how much do I care about bias, how much do I care about variance or sample sizes, and that, someone should be able to input that and say, like cost really matters in this setting. And I sort of agree with you that, yeah, you definitely, in some settings, I think you'd be willing to take a little more bias, a little more, because you'd still be able to capture those trends.
So are there other folks in other countries still using BED method?
That's a great question. I don't think BED is the last time. I should say that I still see many articles being published about it, and especially some of the stuff you were talking about, where people are trying to do mixtures of population. So I think there are people who are trying to make BED work. I don't know if it's actually being used anywhere. I haven't seen it.
The 2005 article from Cambodia that you cited, it's one of our colleagues.
Oh. Well, that's not their fault. Everyone, like my advisor, Dr. Brookmeyer, is on the 2008 article, wherever that is. So people really had high hopes for BED. And it took a long time to really understand. I don't know where those are. Oh, here we go. Yeah, Brookmeyer is on this. So, people had very high hopes. They thought it was, and then they thought, there was also, for a while, there was like a movement to try to trim the tail by like adjusting for it. Like, oh, if we know we're going to misclassify blank number of people, why don't we just subtract those away? Those tend to be very sensitive to getting that correct too, which is sort of the problem. So this wasn't meant to disparage any of those articles. It was just meant to show that BED really was used everywhere, and then it came out. CDC sort of unofficially calls this LAg Avidity assay BED 2.0. Like they treat it as like the newer, better BED. And this Bio Avidity, I think, is actually the most promising of the single. If I were to use just one, I would definitely use that based on at least the data we've seen. It would be very helpful to have other people on their data sets start doing the same type of work so we could start comparing and seeing if we're in the same, validating some of these things. Yeah?
Comment on your last comment is, which I think is really important, is that we're all on the side of science, and so if we don't personalize our involvement in these things, or if we're involved in something, then we say, oh, let's evaluate it and see how well we can do better. And so if the philosophy is we can always do better, then it takes it out of the sort of the personal politics, careerist perspective, and so I really think that actually is a very laudable point. I was going to follow up on James' question. My thoughts were in a similar range about the cost. And I was thinking in terms of the those assays, what the relative costs are, and then questions about like, could there be strategies that would be less costly, but sort of maybe non-obviously.
Right, like targeting specific.
Or something like that.
Well, so these were optimized orders based on data sets. So one thing people are really trying to do is figure out, can we replace CD4 cell count with something else? Because if you could have an equally expensive assay that you could run last, you're going to make a huge difference in the cost. Because right now these are about 3 times as expensive. So the outer ones would be about 3 times as expensive as the inner one, which, you know, that could be a lot of money, especially when you're talking about some of those very large sample sizes. So there's a lot of money being poured into trying to develop new, better assays. I've worked with some assays that are trying to quantify how diverse the virus is in the body, with the assumption being that when HIV infects a person, it tends to be only a few different strains, and then that as the immune system attacks it, it diversifies. And if you can quantify that diversity, that might tell you something about recent infection. That seems to help. Those are, unfortunately, the ones we've worked with are not very scalable right now, in that it's one lab in one place on one data set has done it, and it seems promising. So I think maybe in a few years you'll start seeing better assays or better combinations. The other thing, when you were talking about non-obvious, is sort of, since people were using one cutoff, when we started using these, creating these algorithms, we started creating these boxes, right? Like cutoff, cutoff, cutoff. But there's no reason why you have to cut it like that, right? Like you could take a circle in the middle. So there may be all kinds of places to improve this methodology. I think there's always all kinds of places to improve methodologies, but they're.
Those are good opportunities, actually. I mean, even maybe just working with your existing data set or some hypothetical data sets, or what happens if I remember Ron's job talk, he was talking about what happened, he was comparing public health surveillance if the hypothetical vaccine for anthrax that had better properties than the one that, you can think about like how things might be.
Right, yeah, and we're also starting to play with that with, this way. So in the US, where more and more people are being treated, those fee curves are going to change, right? Like if you imagine that everyone were excluded immediately from the early disease stage because everyone was virally suppressed, then no one would be in this early disease stage. So you have to sort of, just as we're getting these algorithms out the door, we sort of need to move to phase 2, where we start really modeling the probability of viral suppression and things like that.
But although in the US we're close to
right.
getting everyone virally suppressed.
Right. Yes, but I think it's starting to, now that people are starting to get tested earlier and stuff, it's starting to be on people's radar. So I think you need to sort of anticipate some of those future challenges. And we just got so all those data sets were US data sets. We just got Clade C, which is in Africa, data sets. So we're going to start comparing and doing another analyses. We've also been in talks. There's this group called Cephia, which I think is funded by Bill and Melinda Gates, that this whole organization, all they do is this, and they have their own data set, and we've been trying to compare methods with them and compare data sets with them. There's a huge trial, I think in Canada, that we just got approval for like 2,000 samples from them. So I think it's exciting. I think there's a lot of stuff coming up.
Awesome.
All right, thank you all so much for coming.
Thank you.